right, did you guys all want to listen to that for like the next half an hour? I'd probably be okay with that as well, but that'll just be my drive home, just me listening to that on a loop. As if I wasn't going to like listen to it as I played the game all day tomorrow. All right, so we are here today to talk about how you can create bots to play NES games. If you have questions, as you've probably heard repeatedly, you can get on the Slack channel and ask those, and those will be fed back to me. So if you have questions, feel free to go there. A little bit about me. My name is Eric Potter. I'm a software architect for Aptera Software over in Fort Wayne, Indiana. I yak on Twitter at PotterEric. But most importantly for this presentation, I was 5 years old in 1985, which is when the NES was launched in the United States, which meant that this was my first console. This is the console that I remember being the coolest, greatest, most amazing gaming system of all time. And if you don't agree with that, you might want to leave now, because I kind of still feel that way, and just about everything I'm going to say is related to the fact that I still love this console. I had played an Atari 2600. I didn't own one, and so I have fond memories of that, but the NES was the first system I owned. And so when I found out that someone had written an NES emulator that had an API, and I could write code to play these games that I remember so fondly, I was really excited, and I've played around with it a lot. So hopefully you guys have as much fun with this as I do. Before we start talking about the API for the emulator, let's talk a little bit about the NES. It's a really fascinating machine, mostly because even by 1985 standards, it's a very limited computer. It's not powerful at all. By today's standards, it's almost nothing. The CPU in the NES would probably be like the third or fourth most powerful processor on your iPhone. Like the USB controller on your iPhone might be more powerful than the CPU on the NES. Nintendo actually existed for quite a while before they released the NES, which, if you're not familiar, NES stands for Nintendo Entertainment System. That's the console. And I will refer to it as the NES from here on out. But Nintendo actually started its existence as a toy company. They had built a lot of toys and had started to make their way into electronic toys. Some of those great 70s handheld games that had little buttons and blinked and beeped at you and had those sweet LCD graphics. And then they had started to make their way into arcade games. And they actually had an arcade game that had done really well in Japan. The English title is Radar Scope, and they sold a lot of it. And so they thought when they brought it to the United States, they would sell a lot of it. And so they produced a ton of them, shipped them over here. And Radar Scope did not do so well in the United States. And what was very common at that time for arcade games was you would actually have an upgrade kit for the cabinet. It's strange to think about as software professionals that our software would be housed in these giant wooden cabinets. But there was a pretty strong need to not just ship these wooden cabinets every time they needed to update the software. So Nintendo wanted to release an upgrade kit for this Radar Scope cabinet, and they didn't want to spend a lot of time on it, a lot of money on it. They were just trying to recoup some of the lost money on the Radar Scope cabinets. And so they had two engineers and a graphic designer kind of come up with this upgrade kit. It was some minor internal modifications. They actually thought the biggest modifications would probably be the giant stickers that go on the side of the arcade cabinet. And this little team released a little game called Donkey Kong. And the team that they kind of threw together was led by an engineer named Gunpei Yokoi and a graphic designer named Shigeru Miyamoto. And so they had this, with this tiny investment, they had this hugely successful arcade game. Donkey Kong became a huge deal, and its sequels became a huge deal. And at some point, Nintendo wanted to be able to have Donkey Kong in the home. There had been some consoles before this. The Atari 2600 was the one that had sold the best, but there was the Magnavox Odyssey, which I'm particularly proud of because it was designed in Fort Wayne, Indiana. And there was the ColecoVision, which, if memory serves, Coleco stands for Connecticut Leather Company. But you know, if you make leather, then apparently that qualifies you to make video games in the early 80s. Which actually they made a really good machine, it just didn't sell terribly well. But Nintendo wanted to have their own console, and so they released one in Japan initially called the Family Computer, or the Famicom. And the Famicom really is the hardware that we know as the NES, just packaged quite differently. But there was an interesting thing that happened. It actually is really important in the history of Nintendo, but in about 1983, the Atari had gotten so popular that just about everybody made a game for it. I joked around about Coleco getting into the video games industry. There were a lot of video game publishers, especially for the Atari. And so there was this huge problem before the internet where you, as a 12-year-old, you would go to the store to buy an Atari cartridge, and all you would have is the boxes. We didn't have online reviews. You know, there wasn't a big print review operation in place at that time. So you just go to the store and pick one that was fun. Well, there were tons of terrible games, and so the odds of you picking a bad game were pretty high. And so this actually had a fairly devastating effect on the video game industry. It's sometimes called the crash of '83. If you're a video game historian, you probably know all about it. And so Nintendo does something really interesting when they bring the Famicom to the United States. They redesign it to look like a VCR and don't market it as a video game system. The reason that you put the cartridges in the front is because that's what you did with a VCR. And they actually changed the colors. In Japan, the Famicom was this really vibrant red. In the United States, the NES has that classic gray and black look because it looks like a VCR. And it wasn't just to play video games, it was an entertainment system, right? And this was kind of a gimmick to get retailers to stock it, and it shipped with the Zapper, which made it look more like a toy than a video game. It also shipped with a robot. And you guys remember, have you ever seen Nintendo Rob? Okay, a few people. The original Nintendo, when it first launched in the United States, had an optional robot accessory. And that was mostly a gimmick to get stores to stock it, but it obviously, the Nintendo very quickly stood on its own, and that was kind of discontinued. So they had this system that played games, and even by, like I said, by 1985 standards, it's a very limited machine. It actually kind of comes from the design philosophy of the chief engineer. It was this guy named Gunpei Yokoi, he was the lead engineer on Donkey Kong. He becomes the lead hardware engineer on the NES. But he followed this philosophy, which the rough translation into English is lateral thinking. But he says it's a creative, unexpected approach to problem solving applied to outdated, inexpensive, or otherwise off-the-shelf technology. This is a really fascinating idea to us as web developers in 2018 because we like to switch JavaScript frameworks about every 3 months. I mean, there's probably been a new release of your JavaScript framework of choice since you arrived at the theater this morning. And to think about one of the most successful computing platforms of all time, they started with what was essentially a 10-year-old CPU. And all the hardware in it was pretty well understood. It was pretty old. The CPU was manufactured by Ricoh, but it was a modified version of a chip called a MOS 6502, which was introduced in 1975. And even when it was introduced in 1975, it was designed to be a low-cost processor. So this was not competing with the Intel processors of the time. It was an 8-bit CPU, which has kind of become a common moniker for this era of video games. By the time it was released in the United States, the Intel 286 was already out, which was a 16-bit processor. The Intel 386 would be launched very shortly thereafter. So it's really probably a generation and a half behind, even by the time it launches. This processor ran at a screaming 1.97 megahertz, which I think I can actually count that fast. I'm not sure, but maybe. But it's a laughably slow processor. And you might ask, well, why 1.79 and not some other more standard number? It's actually synced up with the refresh rates on TVs of that era. TVs from that era, and actually CRTs, even to this day, refresh about 60 hertz. And so the processor was kind of synced up so that it lined up with that. Actually, in Europe, where they have a different refresh rate, the NES used an even slower processor to be synced up with their 50 hertz refresh cycle. The NES had a sweet 2 kilobyte internal RAM chip. You have to remember that in 1983, when this machine was originally designed, 1 megabyte of IC memory cost about $2,000. So a lot of the design decisions from that point on are based on the fact that they need to minimize the amount of storage in it to make it affordable in the consumer market. That's weird for us to think about because that much memory now is basically free. But in 1983, it was enough money that it would become a hindrance to people buying it. One of the things that Nintendo did very wisely is that the memory that's addressable starts in the internal RAM, but then the address space continues onto the cartridge. So individual cartridges could choose to have different amounts of storage. So when you look up how much storage was in the Nintendo, you always get mixed numbers because it did depend on what cartridge was in the game. This is also how the Game Genie worked. You guys remember the Game Genie? The Game Genie was a device that you would physically plug into your Nintendo, and then you would plug the cartridge into that. What it actually did was it would intercept memory access calls from the CPU to that memory and return different values. So for example, in Mario Brothers, you'd normally start with 3 lives. But that memory location that had the binary value for 3 was in a well-known location. It was in the same spot every time. So the Game Genie can simply return 99. And so the Game Genie actually worked by intercepting these ROM access calls and returning different values. The memory is divided kind of in half between the program ROM and the character ROM. The program ROM, as you might expect, stores the code. The character ROM stores the visual elements. The character ROM is then further divided into an 8 kilobyte addressable space, half of which is for sprites and half of which is for the background elements. And the background elements are almost always made up of either 8x8 or 8x16 pixel mosaics called tiles. And like I said, we almost never want to make copies of things, which actually defines the characteristics of the PPU. The PPU is like a graphics coprocessor. PPU stands for picture processing unit. And it had some really interesting limitations. You could only have 8 sprites visible on any given scan line. So a lot of the games have to do funny things where the sprites aren't quite lined up. Any given sprite can only have 3 colors in it. This is why Mario's hair and Mario's shoes are the same color. I've never known anyone else that coordinated their hair color with their shoes. Mario did, so does Luigi, although they pick different colors. And you can only have 64 sprites on screen simultaneously. Some Nintendo games would kind of game this, where they would actually have more than 64 sprites on the screen, kind of, because they would alternate frames. So they would draw one frame with half the sprites, the next frame with the other half the sprites. And you can sometimes see this visually because some of the sprites look like they're flickering just a little bit. This is way more noticeable on modern emulators with high-def TVs because there's no ghosting on high-def TVs, so they seem to flicker more. That flickering was compensated for by the CRTs because the phosphor that actually emitted the light had just a slight ghosting where the image would stay there for part of 1/60th of a second after it was gone. And so the Nintendo engineers took advantage of that. The one affordance, the one luxury the PPU had that not a lot of other machines had at that time was hardware scrolling. And this is one of those things that by modern standards seems really elementary, and why wouldn't you have that? But you have to remember that not many games had this, and no previous consoles had smooth hardware scrolling. There are some arcade games that did, but not nearly to the same extent that the NES has it. So for example, if you've ever played Pitfall on the Atari 2600, you'll know that you do scroll side to side, but instead of it scrolling smoothly, you kind of move a page at a time. So you get to the left end of the screen, then you go to the next page. And you can move repeatedly, but you always move a page at a time. The PPU actually has a register where you can define where you want to be in the visual space. And what's drawn on the screen is stored in what's called the name table. And the name table is twice as wide as what's rendered on the screen. Now, I say it's twice as wide, but remember, I said that they never make any copies of anything. So the name table is actually just an index table directly back into ROM. The visual elements are never copied out of ROM. They're just indexed. And they end up doing some really clever things like this. I'm going to assume that you guys have all seen this before. But how many of you have ever noticed that those two things are actually the same visual element, just with different colors? I actually had never noticed. I found this out 2 months ago, and my mind was blown. I've spent so much time looking at this. And then some of my coworkers were like, come on, man, you didn't notice that when you were 10? I'm like, no, apparently not. But they're the same elements. Even the clouds and the bushes are themselves made up of these 8x8 pixel mosaics, and the clouds have some additional sprites or tiles beneath it. The other thing is that when the tiles are stored, they're actually not stored with a color. They have color indexes, and then you have a color palette applied to it. So the clouds are those sprites with a white and blue color palette. The bushes are the same tiles with a green a green color palette applied to it. This is actually also how Mario and Luigi are different. The same set of tiles, just with different color palettes. The APU is the last critical bit of hardware inside the NES. It's the audio processing unit. It also is fairly limited. The Commodore 64 actually had a much more sophisticated audio processor. It only had it had 5 channels, 2 for pulse width, 1 for triangle, 1 for noise, 1 for low quality digital samples. And yet they did some really amazing stuff with it. I was playing the background music for World War I in Mario earlier, and there are probably a lot of you like, oh yeah, that's pretty good, I like that. One of the things that Nintendo did really wisely was they brought in a pretty good composer who has since become very famous in some circles, a guy named Koji Kondo, who composed all of the music for Mario and also Legend of Zelda and many other games. But he composed the music for this hardware. He didn't, have other compositions that he tried to port back. No, knowing the limitations of this, he wrote those pieces of music. And they actually hold up pretty well, pretty solid. Let's talk about some of the software in the NES. We're software people. You're at a software conference. One of the things, again, that comes out of the fact that they tried to limit the storage in the NES is that the NES has no operating system. There's no BIOS. It actually doesn't store its own character set. All of that has to be on each cartridge. So the cartridge is responsible basically for everything. There's not even a library to display text on the screen. Each cartridge is responsible for providing that. And they had to provide their own fonts. So like in the upper left-hand corner there where it is displaying Mario, that means that the Mario cartridge is storing the M, the A, the R, the I, and the O. And then it's loading those tiles into memory like it would the tiles for the clouds or the bushes. The other interesting thing is that when they developed these games, they didn't have a C compiler or any other compiler. They actually wrote all these games directly in assembly. The fact that there's no built-in character set, no built-in operating system, and it's all written in assembly means that Hello World for the NES is a monumental task. It's just piles and piles of almost illegible assembly code. And it is very much dependent on a bunch of esoteric but well-documented hardware registers. And you have to know what register to assign a value into for the CPU to talk to the PPU and things like that. Despite that, they came up with these great games. And a lot of the credit for that goes to this former graphic designer who quickly turned into a game producer named Shigeru Miyamoto, and I'm probably mispronouncing his name. But in a very short period of time, he defines a handful of game genres. Super Mario Brothers is the primary early example of the platformer game genre. You can argue there are others, Pitfall maybe being the most famous. But what Miyamoto and his team do with Super Mario Brothers kind of define that genre for a generation. Similar with Legend of Zelda, they essentially define the RPG genre for a decade. And there were a lot of other game designers that came on after and added to it and improved it. But these two games were actually both designed kind of simultaneously at Nintendo's headquarters in Japan. And they were both designed for the launch of the NES in the United States. And if you consider what they did in a fairly short period of time, it's really astounding. One of the things that I found to be really fascinating as I studied what they were doing during that game design is that probably without knowing it, they were following what would later be deemed the Agile Manifesto, which was very different than how a lot of software was being designed in the 80s. In our industry in the 80s, this was when we were in the midst of this big push towards more documentation and more process. This is the time when the rational unified process is born, and we have more and more and more that we have to document before we ever write a line of code. The Agile Manifesto comes later. But as they were developing these games, you see that they would iterate really quickly. They would write part of a world, and then they would play test it. And they would write part of a world, and they would play test it. There's a lot of stories, some of which may be apocryphal, about things they almost put into the game and threw away. One of the things that made Miyamoto such a good designer was that even though he was the director of the game, he was willing to work with his team, and he was famous for arguing for his point of view, and even more famous for being willing to lose the argument in order to let the better idea win. But they did that through iteration and through that constant improvement cycle. The other thing they did that was kind of revolutionary at that time in the video game industry was they had cross-functional teams. A lot of video games were designed such that the developers were kind of in one building and the audio guys were somewhere else and the graphics guys were somewhere else. But Miyamoto brought the whole team together and they would iterate together quickly. There's a fairly famous story about Miyamoto and the developer and the audio designer, Koji Kondo, being together, trying to get the background music and the visual effect of jumping up and getting a coin and the sound effect for getting the coin all lining up. In fact, if you think about it, the sound for when you get a coin, which when I do this for smaller audiences, I will often try and mimic it, but I'm not going to because also this is being recorded. But in your mind, think of that sound. Okay, everyone really quick. Okay, you hear it? You hear it in your mind? That is in the same scale as the background music. It's actually the first and the fifth of the scale that the background music is being played in. So with these agile teams, with iterative development practices, they really release some great software in a hurry. So with that as background, about a year ago, I stumbled onto a little project called Nintaco. It's a sweet name, isn't it? It's got a pretty nice logo, actually. Nintaco is an NES emulator, of which there are many. And there are a lot of good ones out there. But Nintaco is different in that it has an API. Nintaco itself is a Java application, but the API is exposed through a TCP/IP interface, meaning that you can write code that interacts with the NES emulator from any other language, as long as you have the access to connect the TCP/IP. And let's see if I can do this. Oh, it's not showing up. All right, I'll come back to that. So Nintaco is it's a very full-featured emulator, actually, and the gameplay is pretty good. It works with USB gamepads. It has tools for creating tool-assisted speedruns. You can actually manipulate the memory inside the NES. So if you want to do Game Genie-like hacks, you can. But you can also write some code to play the games. And turns out this is one of those things that is like kind of a sweet spot for me because I both love to write code, especially in C#, and I love NES games, so it works out pretty well. I'll walk you through some of the code that you need to write, and then we'll actually look at a demo. So the Nintaco emulator, which if you Google for Nintaco, you will find it right away, is hosted at nintaco.com, and it's just a Java app, and the guy that wrote it goes by 01, and his coding ability is apparently really good because he developed this entire emulator, but for reasons he doesn't say, he apparently doesn't like Git, and so you can get all the source code for it, but it's just a zip file on his machine, or on his website, which isn't that difficult. And if you want to consume the API for it, there's another zip file that you can download. With his permission, I did create a NuGet package for the C# wrapper around the API. So it's his code. I just contributed it to NuGet. And so if you want to write a little bot to play an NES game, you just have to download that NuGet package. It's called Nintaco proxy. And then with that, you can start to develop a bot. I'm going to continue to use the term bot. Some people have asked me why I don't call it an AI to play a game. The main reason I don't is that the I in AI stands for intelligent, and none of mine are at all intelligent. I guess neither am I. Maybe that's the problem. But it's kind of fun, so we'll just call them bots. To get started, there is a singleton called API source, and you need to call the init remote API method on it and pass the port, which that port would be available to you when we launch the emulator. I'll show you that in a little bit. But it defaults to 9999. The way that you are typically going to interact with these NES games is you're going to respond to events. You're going to have event listeners. The two listeners, or the two events that I primarily have worked with, are the frame listener, which fires off an event every time a frame is rendered. So the PPU draws out an entire screen, and it has it all configured, and then you have a chance to have an event that fires right at the end of that, so before the next frame starts. There's another API here that I'm adding a listener to for API enabled that simply fires once when you first connect to the emulator, and that's really useful for storing the current time or initializing other stuff. There are other events that you can respond to. There's a scanline listener that is like the frame listener, except it fires at the end of every scanline being rendered. There's also a scanline cycle listener that is fired at the end of every dot being drawn. So that would happen all the time. There's a control listener that happens after an action happens on a controller. So let's say you push the A button, you have a chance through the API to take an action before the emulator gets that button pressed event. So maybe you want to, I don't know, have some kind of key combination. There are some other events that you can hook up to when the API is deactivated or when the emulator stopped, things like that. But what I want to focus on today is just looking at a simple bot that is kind of just going to push buttons. You could also have more intelligent bots that look at what's going on the screen. That's beyond what I want to talk about today. The API does allow you to inspect the ROM or the internal RAM values. And so if you wanted to check on the position of an enemy, you could do that. You would just need two things. You would need to know the hex value of where that location is stored, and you would need to know something about what hex value is stored at that memory location. It's pretty esoteric to look at it. It's kind of fun to try and figure out what the different hex values mean. There are actually websites out there. I think there's romhacking.com. I've got a link to it later, where people have documented for various cartridges what the various what the various memory locations hold. But today we're just going to look at a little emulator that mashes some buttons. Now, one of the first things you notice when you start to write a bot is that you probably want to do something for some amount of time. You probably want to push the left arrow button for 2 seconds. And so the first time I tried to do this, I pushed the button, which I guess I didn't talk about it, but it's pretty simple to push buttons with the API. There's a write gamepad method, and you just tell it which controller and which button you want to push and pass it true or false to set the button state to up or down. So you can push a button, and you might say, well, I'll just wait for 2 seconds, and I'll set the button state to up. Except, remember, the NES was single-threaded. And so the way this emulator works is if you do a thread.sleep for 2 seconds, you will lock the entire thing for 2 seconds. So what you have to do is you have to write a little state machine to handle your frame event listener, and you just have to wait for 2 seconds to be over, and then have the button set back to false. If you've ever done any other real-time programming, maybe for Arduino or other microcontrollers, there's a similar concept. In the Arduino, if you do a thread.sleep for 2 seconds, you will not get any I/O from the rest of the world. You know, if you're listening for I/O on one of the pins, maybe from a temperature sensor, while you do that thread.sleep, you won't get any of those temperature values because you're basically locking down the only thread on the very limited machine. Nintaco is kind of the same way, where if you do a thread.sleep, you'll just lock it all up. And it's really obvious when you do it because the emulation suddenly stops until the time has expired, and then it carries on, but then your timing is all wrong. So kind of what you have to do is you need to check the clock, which the easiest way to check the clock is to look at the frame count. And because we know that the NES runs at 60 frames per second, we can kind of work the clock back from that. And so when the API is first initialized, we can kind of check that as the beginning of time, and then everything else works off that. So then the frame event listener will get called every 60th of a second. And so we have to set the button state what we want based on the fact that we're getting called repeatedly. And we have to keep track of what state we're in. So let's look at some code for that. Maybe. See if I do this. There we go. Yep. That code's really big on that giant screen. So this is some code that will play the game Bomberman. And if we look at the main method, you can see I'm just initializing that remote API. And you would see if I was going to start Bomberman. That's kind of obnoxious. Actually, I like it, but it's hard to hear. What I would want to do is come up into the Tools menu and start the program server. And you can see here that it's telling me that the address and the port. So I just need to use those values. So then I'm going to call this launch method, which in this case I'm actually registering a handful of events, but I really only care about the frame listener and the activate listener. And so if we look at this render finished method, you'll see there's a little state machine here. I have 4 states. I want to move right, I want to drop the bomb, move left, and wait. And then what the state machine will do was it will check the state, and then based on that state, take an action. And if it's time, then we'll transition to the next state. So let's look at what would happen here. You guys want to watch me play Bomberman for like the next 10 minutes? All right, so I'll start the program server and hope I don't die before I get there. Oh, apparently I died. All right, let's try that again. Like I said, drop the bomb. Oh, I'm gonna blow myself up again. This is why they're called bots and not artificially intelligent. My bot will run kamikaze into the enemy. So here's what's supposed to happen. You move right, drop a bomb, move left, wait for it to blow up, and start the cycle again. pretty fun. And as long as you don't, like I said, as long as there's not an enemy there, it will eventually clear this entire level. All right, enough of that. Hey, I said stop. There we go. And we could certainly make that bot more intelligent, but it serves the purpose. So basically what this is going to do is it's going to, if we're in the move right state, we are going to set the right gamepad state for the right button to true on the first controller. And this simulates the pushing the right arrow key. One of the things that's noteworthy about this is that the button states are reset for every frame render. So if you want to continue to push the button for a second, you have to set the state to true for 60 frames. And in this case, I'm doing a calculation based on if the frame count minus the start frame is greater than the space traversal time, which if that is true, then we'll set the state to drop a bomb and then reset the current timer. Dropping a bomb actually does not take any time. You just have to hit the button once. And so in that case, we'll hit the button to drop the bomb and then move directly into the next state, which is move left. We'll move left. Again, this looks exactly like move right, except we're hitting the left button instead of the right button. And then we have to wait for a little bit of time to wait for the bomb to blow up, then we can start the whole thing over again. Now, one of the things that we could do to make this more intelligent was we could start inspecting those ROM values. Which, oh, I died. Come on. Normally, I should get a menu up here at the top that has a... Let's try it again. Yeah, so the Nintaco emulator has these debug tools that allow you to actually inspect into the memory of the game that we were talking about. So let's do this. Let's open up Mario. And we'll set him to be a little larger. And we could go ahead and read some of these memory values to figure out the current location and whether he's facing enemies. It's not very interesting in a presentation because you're just basically manipulating hex values. But if you can see these hex values are updating in real time. And there are tools also in Nintaco for you to search for specific values. So maybe you know that currently you have 3 lives, so you can search for the hex value of 3 and try and figure out what it is. Or like I said, you can try and find online what's there. Some of the other interesting tools that are available to you is that we can look at the pattern table. So if you can tell, this is all of the 8-bit tiles that make up everything that's on the screen. You can see, like I said, the character values are up here. It actually has to store the 0. Here are the set of tiles that they use for the clouds and the bushes. And you can also notice there's this tile right here that is alternating color, and that's actually alternating the color of this coin up here in the top. Another interesting view is that you can see the name table. Like I was telling you, NES has some really interesting hardware scrolling. And so you can see what's actually being stored inside the PPU is larger than what's being displayed on the screen. And you can actually kind of see as it scrolls it's redrawing the memory that's off screen so that when you scroll to it, it's ready. The other thing that's interesting about this is that it will show you the individual tiles. So we were looking at the clouds earlier. You can see here are the collection of tiles that make up that cloud. And the sprites are stored a little bit differently. That's in the OAM table. And so you can actually watch in real time as the sprites update. So when Mario gets the mushroom, he goes from being 8 sprites to 16 because he's now larger. And the Goombas show up and then also leave sometimes. So with a little investigation, you could dive in and start to make the bot more interesting and smarter and make better decisions. That Bomberman bot should be able to detect that it's about to run kamikaze into one of the enemies and turn around. It should also be able to detect whether or not, like if it's run all the way up against a block that needs to be destroyed. In Bomberman, those blocks you blow up are actually part of the background, and so we would have to look for those in the namespace table because the namespace stores the background. The enemies are sprites, and so they would show up in the OAM table. But we could look for those things and figure out where they're at and make better decisions. So before I wrap up, do we have any questions? Yeah.
Do you have a Mario bot ready?
Do I have a Mario bot ready?
Yeah.
Not that I'm willing to show. It's terrible. The reason that I did the demo with the Bomberman one is it's that really simple 2D grid. Getting the timing right for Mario jumping over that first Goomba is a little bit tricky because you don't know exactly when you are going to encounter him is based on when you start moving. I do have some really sweet bots that will run kamikaze into that Goomba over and over, but I don't really like him. Other questions?
Is it possible to create a bot that can modify its own state to like learn better? Like in one application, they like, oh, I died here. Maybe I'll try to do it again.
So I think what you're actually asking is, could you apply machine learning to an NES game? Is that essentially it, right? Sure. So you certainly could. It would be a machine learning exercise much more than a bot programming exercise. It would actually be a lot of fun. It would be really interesting to throw like the Azure machine learning algorithms at it and see what it would come up with. Some people have done some research on that and have shown that these games are what they call NP hard. So it would take a long time for it to figure out a good solution, but in theory it would work. And it would be a heck of a lot of fun to try. I don't know if there's any real value in it, but man, would it be fun to do. Other questions? All right, let's see if I can get this to show up again. All right. If you are more interested in this, these are the 2 books that I recommend. Jeff Ryan's Super Mario is an interesting read. At least it was to me. It follows Nintendo's corporate history through the story of Mario. And he goes into a lot of depth about some of the design decisions they made about the game. And that story about upgrading the radar scope cabinets to be Donkey Kong cabinets was really interesting. One of the really interesting things that Miyamoto does with Mario that was considered controversial at the time is that in the original Donkey Kong, Mario is the protagonist, and then in Donkey Kong Jr., he's the antagonist. And then obviously in Mario Brothers, he's the protagonist again. And so that was kind of a different thing for a video game to do, to have a character switch from being the good guy to the bad guy and then back. There's also another story of the game that became Super Mario Bros. 2 in Japan. Have you guys ever heard of this game? It's notoriously difficult. Miyamoto kind of tortured the players. He thought it'd be really funny where, like, the first time you encountered a mushroom, instead of making you bigger, it would actually kill you. And you can find copies of it online for purchase. But that book is really interesting, covering a lot of his thought process, and it actually goes almost up to modern day. I think the game was written while Wii was still the newest console. And so he follows the development of Mario all the way up through the Wii. There's another book called I Am Air that is a reference to Legend of Zelda. He does talk a lot about translation and the issues between the American audience and the Japanese audience. That's really interesting. I Am Air is famously what one of the villagers in Zelda 2 says to you, and most people thought that that was a mistake. The programmers actually intended it for that to happen. They just thought that the joke would come across more clearly in English. There were two villagers in that village. One was named Bug and one was named Air. In the Japanese version, it's clear that it's kind of an inside joke. In the American version, it just looks like a programmer mistake. I Am Air is a very technical book. It does have the complete assembly code hello world for for the NES. I really enjoy that, but know if you pick up that book, it's going to be really nerdy. If you're interested in this, go out to nintaco.com. That is where you will find all the downloads. You can get the emulator itself there. There is pretty good documentation both on the game and on the API. That is also where you can download the source code for the emulator if you're interested in that. If you want a longer explanation of that Bomberman bot that I built, it's available on my blog at humbletoolsmith.com. And if you want to develop bots that are more sophisticated, that actually inspect memory values and make decisions on them, you can go to romhacking.net. That has a lot of documentation on what specific memory addresses mean in different games. And it's surprisingly complete for the games that are documented. That being said, I know this probably wasn't the most practical session you will see today. I have actually used this as a teaching tool to teach C# to some other developers, and that was pretty effective. I hope you have fun with it. That was the main thing I got out of it, was just playing around and trying to write code to do this. Thinking about code in a different way, thinking about how to write code in a single-threaded environment. And writing code where the debugger actually stops everything, locks up the whole emulation. If you want to chat further, I would love to yak about this stuff, either about the emulator or about Nintendo history. I'll be hanging around up here for a while afterwards or out in the hall. I hope you guys had fun with this. I hope you guys explore it, and thanks for coming.